In Module 4.1, we introduced the derivative and came up with a definition for it. That's not a terribly efficient method for calculating derivatives. Those problems all tend to be quite a bit cumbersome. So what we want to introduce in this module now are some properties, some theorems that will allow us to calculate derivatives more quickly so that we can start talking about applications, getting to our results more quickly. So when we're talking about the derivative, keep in mind that that's the exact same thing as the instantaneous rate of change of our function. Which is the same thing as the slope of our function at some specific given point. So again, what we're talking about is how quickly our function is increasing or decreasing at some specific point. So before we get into these theorems, we want to talk about some different notation that we'll use interchangeably, the book will use interchangeably, but each of these notations mean exactly the same thing. So in the last module, we used this notation, f prime of x, which means take the derivative of our function with respect to x. Similarly, we could write y prime, which would mean take the derivative of some equation y equals whatever we have on the other side. We could write dy over dx, which means exactly the same thing as y prime. We were given some equation y equals whatever on the other side. We're going to take the derivative of that equation y with x as our independent variable. We could also write d over dx of f of x. So this means take the derivative with x as the independent variable, or with respect to x, of this given function f. Or another way to write that same thing, which we probably won't encounter until later on in this course, but I'll go ahead and introduce it now, is f sub x. So it means, given this function f, take its derivative with respect to x, or with x as that independent variable. So again, all of those notations mean the same thing. We want to take the derivative of our given function. So we have several theorems we want to introduce, which again will allow us to essentially take a shortcut to calculating derivatives of different types of functions. So first we have the constant function rule. And this rule tells us that the derivative of a constant c is always 0. So if we're taking the derivative of some constant c, so c is some number like 2, 47, the square root of 53, the derivative of that is always going to be 0. And the idea here is that if we're considering the function y equals c, that again is just going to be a horizontal line. As we move left and right across the x-axis, our function value never increases or decreases, that's just remaining constant. So a horizontal line has no slope, so the rate of change of a constant is always just going to be 0. We have one property here that isn't provided in the textbook, and that's the derivative of x. So the derivative of x is always just going to be 1. And again, we can look at visually or graphically what we're saying here. So if we're considering the graph of y equals x, even though we don't always write it there, we know that there's a coefficient of 1 and a y-intercept of 0. So whatever the coefficient for x is, that's the slope of this line. So in this case, our slope equals 1. So anytime we're dealing with y equals x, that rate of change is always 1. So anytime we have the derivative of x, we know that that's 1. The power rule tells us that for any real number, n, the derivative of x to the nth power To evaluate that, what we're going to do is take that exponent of n, bring it down in front of our original function. So we just bring that value, that exponent, down in front of the original function, and the original exponent gets raised to the n minus 1 power. And then all of that will be multiplied by the derivative of x, which, as we just established up here, the derivative of x is always 1. So we always apply whatever rule we're given and then take the derivative of whatever this interior base function is. So eventually this will become a more complicated component. We'll be raising a polynomial expression to a power, look at other more complicated expressions. But for right now, we're looking at x raised to the nth power. So that exponent just gets dropped down as a factor in front, and the original exponent gets reduced by 1. And then we multiply by the derivative of whatever that original piece was. The constant multiple property tells us that for any constant k, if we're taking the derivative of that constant times a function, this constant doesn't have anything to do with x. It's just a number. So we can bring that out in front of the derivative and just focus on taking the derivative of that function, or the portion of that function that has something to do with x. So any constant can be pulled out front of the derivative. We can just set it aside until we are completed with evaluating that derivative. And then we have the sum and difference property. So if f of x is composed of the sum or difference of two functions, so if we had u of x plus v of x or u of x minus v of x, either of those two options, then the derivative of our given function would be the derivative of the first function plus or minus the derivative of that second function. So if to start off we had an addition problem, the final result is an addition problem. If we started off with a subtraction problem, the result here is a subtraction problem. So we're going to continue introducing more properties throughout the semester, but this gives us our first batch. And what we want to notice is that these properties, for instance, if we look back at the power rule, now has absolutely nothing to do with using the definition of the derivative, doesn't have anything to do with limits, which makes these problems quite a bit easier to work with. So for now, we can take a break from limits and start applying these properties. We're not done with limits. We will come back to those ideas. But for the next several modules, what we'll be introducing are different properties to evaluate derivatives without having to go back to that limit-based definition.